Hello, hello.
Hello.
Okay, let's begin, everyone. Everyone knows that you're sitting, but please feel free to sit anywhere. Like I said, you only need to go back to your team when for the lecture summary at the end. So I'd like to bring up my daily lecture summary as usual. This is every day. So, and I advise them to really look at the lecture summary, the daily lecture summary every day. I have posted the extra lecture with the videos, and this is directly related to Fourier series, Fourier analysis. That's the new, the big topics for the second half of the semester. And so we'll address that topic, soon after the motivation. And I'd like to, maybe I can stay on this and go down. So please fill the midterm feedback form, because I would like to address any issues as soon as possible. As you can see here, I already started to do something. I do read the midterm feedback regularly. So, and I was surprised to see that one student, just one, did not see the hierarchy of my lecture notes. And so I mentioned that you need to, there's several places where you can look at, right? The list of topics, that's a separate link. Let me show you, that's in the list of topics. Let's see, in the portal, you can access that through the portal, right? And this is the portal. And this is the list of topics here. When you go into the list of topics, my lecture notes are listed in order. Okay, and you can also use the list of topics to search. For example, by keywords, right? You have keyword generalized eigenvalue problem. Click over here and find. Then you find the corresponding section. You can do the same in the daily lecture summary as well. So there's several places. Now, but there's more than that. Okay, more than that. In that, in this meeting 21 here, which is videographed at 10.3.40, I talk about the flowchart that Jackie brought up, and the flowchart is essentially the table of contents at the beginning of each section, right? So if you bring up this and then go to around time of what I did in class, and in fact it's ready here for you already, okay? And it's in the form of the table of contents at the top of my lecture notes. So let me bring it. Okay, so I'm not going to rehash that. It's videographed. You can watch and rewatch as many times as possible. Okay, so please, and there's more. I also refer to that flowchart in a subsequent meeting. Meeting 23. Okay, so there's one regarding the big picture. One student So the big picture, I have it in the first half of the semester as well, but right now in the second half, there's a really, really big picture that will come up very, very soon. That is to motivate Fourier analysis, projection, right below, meaning even in this today's planned lecture. That's regarding dynamic finite element analysis, earthquake, fast Fourier transform, how to deal with general non-simple function excitation, when you solve the dynamic problem. And what does it mean non-simple? Logarithm of 1 plus x, for example. Okay, so big picture is always there. Just ask if you have questions. Okay, next, I have mentioned that I posted the extra lectures with the videos. That's section 8A, okay, on Fourier series, and linear second order ODE that we will address soon. And now I'd like to bring up my handwritten notes from last time, meeting 28, just to wrap up this excellent question by Jackie. How do you transform the generalized eigenvalue problem to standard eigenvalue problem when you have mass m1 different from mass m2? And I took a simpler example than Jackie's example. I have already presented the method, and now I just want to wrap up with method 3. Okay, method 4 was very simple. Method 4 is by pre-multiply by m inverse. Okay, and the new stiffness matrix is m inverse times k. Whereas I'd like to wrap up with method 4, and method 4 is by doing a method 3, multiplicative decomposition of m into square root of m times square root of m. Actually, m to the power 1/2 times m to the power 1/2. And because of the fact that the mass matrix is diagonal, it's equivalent to taking the square root of the diagonal coefficients. Okay, so let's see how what's the end result, and then look at some numerical examples. So I have mentioned to you that this is a quick reminder here. If you pre-multiply the generalized eigenvalue problem, right, by m to the minus 1/2, then you can cancel one of the factor m to the power 1/2, so that the end result on the left hand side is m to the minus 1/2 k times phi, and on the right hand side you have beta m to the power 1/2 times phi, right, the eigenvector phi. And now define m to the power 1/2 times phi by as a new vector c of psi. Okay, then inverting, then you can express phi or phi in terms of psi. Right, so phi is equal to m to the minus 1/2 psi. Okay, and the reason is because this is still not symmetric. Okay, and over here you still have m to the power 1/2 and not identity. So we want to have identity on the right hand side so that it's a standard eigenvalue problem. So once you obtain phi in terms of psi, you can replace over here, and you can sort of see the symmetry popping up, right? And so that's what I want to continue here. Okay, so let me bring up my, this is from last time, so I can just copy from here. Alright, so let me just take this off here. and we don't need all of the details, so let me simplify. Okay, all we have is just, this is the result from the last meeting 28. And yeah, so this part you can leave it here. And so replacing, let me note down here, replacing fee or phi in terms of psi, the new eigenvector in the left hand side we have. Okay, so so what do we have? We have the following. Right, so replacing phi or phi by m to the minus 1/2 times psi. Okay, intuitively you can see that there is some symmetry already, right? M to the minus 1/2 k, m to the minus 1/2, and we will verify that indeed that's the new stiffness matrix is symmetric. And then on the right hand side you only have beta times psi. Okay, and that's it. That's the standard eigenvalue problem with the new stiffness matrix K bar. Use a darker line style. So this is K bar. Okay, so let's throw in some numerical example just to, you know, for many it would be more concrete for you to see the numbers. Right. Let's look at method 4 first. That's a method that is not nice. It leads to a non-symmetric stiffness matrix, and let's recall that for that method, it's actually written here. Okay, K bar is M inverse times K, and so what was M inverse? Recall that M is 4009, right? So M inverse is 1/4, 1/9. You just need to invert the diagonal coefficients, and K is the famous matrix that I have used many times already. And if you multiply this out, it's like, as I already mentioned before, it's like taking the coefficient 1/4 multiplied by the first row and the coefficient 1/9 multiplied by the second row. Make sure that you know how to do that. If not, please come to see me. Okay, so otherwise I would write the result immediately here. So to move on, so that's 2/4 minus 1/4, and then minus 1/9, 2/9. Okay, and clearly this is not symmetric. Okay. So that's the example for method 4, and now let's look at the example for method 3. And for method 3, the K bar. Let me do the following, and then the me construct the equation here and then I'll move it to the next page. Okay, so K bar is that. And then let's copy down here. Okay, so what is, you remember what was m to the power 1/2? M to the power 1/2 is just by taking the square root of m, right? So that's 2, 0, and 0, 3. And now you have the power minus 1/2, so that means the inversion. Okay, maybe let me write down so that, you know, we call that m was 4009, and so therefore m to the power 1/2 is square root of 4, that's 2003, and so therefore m to the minus 1/2, we just compact so that I have more space. I'll rearrange later. Let me just put it down here. Okay, and that's simply active learning credit. Anyone? Is that John? Okay, and David. Now I do a little differently. Anyone who raised my hand, I mean, anyone who raised hands will get to participate. Okay, so John, go ahead.
1/2, 0, 0, 1/3.
Okay, what team number? Team 5? Is it
4.
Team 4. David?
Yeah, that's right.
Repeat.
1/2, 0, 0, 1/3.
1/2, 0, 0, 1/3, and that's Tony, right?
Yeah, it's 1/2, 0, 0, 1/3.
David is team 2, and Tony is
7.
team 7. Very good. So I have more customers, even, right? More people who would participate. Very simple. Maybe let me ask David, what's the principle behind, why do you know that it's 1/2 and 1/3 on the diagonal?
Because that's going to be the numerator.
Yeah, it's just because M is diagonal matrix, so the inversion of a diagonal matrix is just by inverting the diagonal coefficients. Okay, very good. So, so let's compute K bar. Anyone? Okay, David. Let me lead by suggesting something, because then you can all learn a lot. Okay, so let me prepare the matrices first. Right. Now let's, David, let's do this part first. Right, m to the minus 1/2 times k. And not giving me the number, but tell me how do you do that? What would be the principle behind, if you take a diagonal matrix times another matrix, what would be the operations, you know, in the conceptual level rather than numerical level? That's what I just did at the beginning of this lecture. If you take a diagonal matrix times this matrix, it's like taking the first coefficient multiplied by the first row, and then taking the second diagonal coefficient multiplied by the second row. Okay.
So the street fight.
And so therefore, Street fighting method, yes. So therefore this is like 2 divided by 2, minus 1 divided by 2, minus 1 divided by 3, and 2 divided by 3, okay? Now, active learning credit. You take this matrix, multiply by from the back, not from the front. You know, the first part, you take a diagonal matrix and pre-multiply by k. You get this result. Okay. Now you post-multiply by the diagonal, another diagonal matrix, which is also m to the minus 1/2. What is the conceptual operation before talking about the numbers? Anyone? What would be the conceptual operation? You just take this matrix times this diagonal matrix. If you pre-multiply a matrix by a diagonal matrix, the result is as if you take the first diagonal coefficient multiplied by the first row, second diagonal coefficient multiplied by the second row. Now, if you post-multiply, meaning if you multiply from behind,
You do the opposite.
It's a similar thing.
You just do the opposite.
the opposite, okay?
Come to the opposite direction.
Robert, and let's start with you. What is your team number and name?
Unit 1, Austin.
Austin, okay.
Use the columns instead of rows.
Columns instead of rows, Robert.
You do the first row times the other first row as the second row.
First row times first coefficient, second row times second coefficient, okay. So Austin, Austin said it's like you take the first row times the first coefficient, first column times the first coefficient, and second column times the second coefficient. You need to know why, okay? The reason is because if you take your matrix multiplication is you take the first row times the first column, right? But then because of the 0 here, it's only this coefficient multiplied by the first diagonal coefficient 1/2. And then the second row multiplied by the first column, you see, only this coefficient multiplied by 1/2. So therefore only the coefficients in the first column that is get multiplied by 1/2. So what I'm trying to say is the following. When you post multiply by a diagonal matrix, the first column, right, becomes, let me write it in such a way that you can see. So 2 divided by 2, and then multiply by 1/2, okay? And then minus 1/3, multiply by 1/2, okay? That's the first column. And then the second column, if you repeat the same thing, right? For this coefficient here, right? This coefficient is the coefficient 1, 2, called row 1, column 2. So row 1, take row 1 times second column, you see, only this coefficient get multiplied by 1/3. Okay, so therefore, you have minus 1/2, so I can just copy the whole column here, okay, move it down a little, and so this gets multiplied by 1/3, and this coefficient gets multiplied by 1/3. So pre-multiply and post-multiply, you don't get the same thing, okay? And this. Okay, so that's that's the result. But the important point to make here is that you have symmetry. Okay, complete symmetry. And so so that's this method here, method 3. Okay. Now note that the standard eigenvalue problem, after you solve for the eigenvalue and the eigenvectors, the eigenvalue would be the same, but the eigenvectors are not the same. Okay, you get psi instead of phi. So once you have psi, you need to convert back to psi. To phi psi. Okay, just by using this this formula here, right? Phi is equal to m to the minus 1/2 times psi of c. So the method is a bit more advanced, complex, but leads to computationally more efficient because the matrix is symmetric. Okay, the stiffness matrix is symmetric. Okay. So that's complete this part. This active, this critical thinking. I should mark down here. This is critical thinking questions. Is Kyle here? I don't see Kyle. So Kyle asked this question, so I'll skip it if unless someone wants me to explain. This is about the pendulum. How to derive the equation of motion for the pendulum. You can also look at the the solution guide. Kyle asked this question, but this is a very nice question. There's a solution guide in the form of best solution, best reports from last semester. So if no one has question on this, I'd like to move on to this part. And then once you know this part, you can answer this one to get active learning credits. So here, the question, the critical thinking question that I pose myself is that can you concoct a 2x2 matrix with real coefficients, but with complex conjugate eigenvalues? Okay. And as I explained and give an example on Piazza to get 5 active learning credits, and here I give a hint here. I found the following matrix: 1, 1, minus 4, 1. And this is a link to Wolfram alpha. If you click at this, you will see the result, and the result is the following. You have 2 roots, lambda 1 and 2 equal to 1 plus or minus 2i, meaning lambda 1 is 1 plus 2i, I is the imaginary unit or square root of minus 1, and lambda 2 is 1 minus 2i. Okay? Let me demonstrate to you. If you click at this link here, then it would bring up what I type in Wolfram alpha, and the answer is right here, the eigenvalues, right? So 1 plus or minus 2i. So this is a complex conjugate pairs. And how did I find that? And this is the hint here. The way I found is the following. So start with a general matrix A, B, C, D. Okay? You can find the characteristic equation in terms of A, B, C, D. What is the characteristic equation of a matrix? Can someone mention? This is a review, by the way. The characteristic equation of a matrix with the coefficients A, B, C, D. Okay, what I'm saying is the following. If you give a matrix, let's call it A, for example. With the coefficients A, B, C, D. What is the characteristic equation of this matrix? It's basically determinant. Very good. So Kevin, what determinant, Kevin?
I don't understand the matrix.
The determinant of the matrix, Kevin, is team 7, right?
Yeah, AD minus BC.
AD minus BC. Okay, almost. This is, remember the characteristic of linear second order ODE with constant coefficient? It has to have some lambda, right? So let's see, Frank and Devan. Okay, Frank.
Is that when we took the
k minus beta m, the van.
Same thing as you want to take determinant relative to zero.
Determinant of what?
Determinant of the generalized eigenvalue. Or
Determinant of the generalized eigenvalue problem, meaning a minus some
A
beta m.
minus beta of whatever your other matrix is.
Okay, so here, if you are given only a matrix, you know, you're not talking about generalized eigenvalue problem, you're talking about standard eigenvalue problem. So the determinant, the characteristic equation is the determinant of A minus lambda I. The mass matrix is identity, okay, equal to 0. This is the characteristic equation. Remember the Wolfram alpha, you know, several lectures ago. A, okay, of the matrix A. When I lecture on standard eigenvalue problems, you did see that in Wolfram alpha. So you can easily find the characteristic equation. Let me note down the van, and the van is team 6, right? And Frank is team 7. I get to know many of you by now. Can you tell me the order of the characteristic equation? What would be the order of the characteristic equation? Anyone? Quadratic, right? Second, yes, the van.
The order of the characteristic equation is quadratic.
Yeah, quadratic, very good, very good. Okay, so you can express the quadratic equation in terms of A, B, C, D, and that's what I noted down here. Okay. Right, in terms of ABCD, and then essentially you can assume two roots that are complex conjugate, and this is my assumption here, 1 plus or minus 2i, these are two roots that are complex conjugate. Find the characteristic equation in terms of the two complex conjugate roots, these two complex conjugate roots. Active learning credit, how do you, if you are given two roots, okay, how do you find the characteristic equation? This is a different question. The first question was, given the matrix, find the characteristic equation. The next question is, given the two eigenvalues or the two roots of the characteristic equation, find the characteristic equation. How do you do that? This is going backward. Kevin, team 6.
Set both of the set lambda 1 and lambda 2 equal to 0 and multiply them together.
Lambda 1.
And lambda 2. So lambda 1 minus 1 plus 2i. And
Yeah, you can say lambda minus lambda 1, right? Maybe this is what Kevin is trying to say. If you know lambda 1 and lambda 2,
minus lambda 2.
lambda 2 equal to 0, right? That's it. This is the characteristic equation. It's also second order. Okay, but this time you know lambda 1 and lambda 2. Why do you do this? Because you can identify the two characteristic equations. Okay, and then you can back out what should be the coefficient A, B, C, D, so that you would obtain the desired eigenvalue. Okay, so that's the game. So meaning, okay, recapitulation here. There are two ways. I mean, you approach by two different points. The first is because you don't know the matrix, so you give the matrix that has the coefficient A, B, C, D to be determined. How? Well, find the characteristic equation, which is a quadratic equation, in terms of A, B, C, D. Next, give yourself a pair of complex conjugate roots. Okay. And here I just chose this as an example, these two, so 1 plus or minus 2i. Then find the characteristic equation that produce these two roots. Okay? And so all you need to do next is to identify the two characteristic equations, and you have how many equations for how many unknowns? Active learning credits. How many equations for how many unknowns? Come on,
Two
raise your
equations,
hand.
two unknowns.
Two equations, two unknowns.
Well, you know lambda 1 and lambda 2, right? Is that
How
what
many
you-
unknowns do you see up here?
One.
A, B, C, D. Right? You don't know A, B, C, D. You want to find A, B, C, D.
I thought we did.
4 unknowns. Okay? How many equations? 2, because the quadratic equation would have the form of, you know, if you multiply out, you would see that it would be lambda square. I need to use a different symbol now because A, B, C, D is already used. You know, plus some A, B, C, D, maybe F, lambda, plus G, something like that. Okay. So the two equations coming from identifying the coefficients of lambda and the coefficient of 1, right? G, F and G from both characteristic equations. You have two equations, 4 unknowns, means that there's a lot of possible solutions. Okay? And that's how I found this matrix 1, 1, 1 minus 4. You know, let me zoom in here for you to see. Okay, as an example of a matrix that would have a pair of complex conjugate roots. So once you understand this method and can reproduce this example, then you can answer the previous this critical thinking question for active learning credits. Okay. You can also answer this completely answer this question, number 12 on Piazza, and also answer number 11 on Piazza for active learning credits. I hope someone can do that. I already showed you the method there. Okay. A really big picture. Okay, real world application of we are getting into dynamic finite element analysis. You have seen actually a simple model in the first half of the semester. You can think of this as an example of 3 bar elements, right? In series, okay, and each element has a spring and a damper. That's already finite element, and we did the dynamic aspect of it already. And in this particular example here, which I have shown to you, and I'm not going to talk on this again, you have seen the different eigenvectors. Okay, whenever you see this, you think eigenvectors. All right, this is the first mode. This is the fundamental mode, and you see in this example here, that's much more complicated than the 3 bar elements in series, right? That we use in the first half of the semester. Each node here has 2 degrees of freedom. You count the number of nodes, you multiply by 2. That's how big your stiffness matrix would be. All right. And you know the vibrational mode shape is also more complex. Okay, that's closer to the real world example already, and you see Tim Byte code, the finite element code, you know, this like this, and this could be a model report as well. Okay. So anyway, let me leave it here. Close a few. Right, but I'd like to show to you something that is also even more advanced. You get into the Wikiversity page, and in the first link, you have this. Okay, this is the vibration of a shell structure. An example could be, the body of a rocket. In fact, the development of the theory of shell, cylindrical shell, was because of interest in building rockets. Remember when von Braun experiments with, I think it's called probably the V2 rocket, not the V1. V1 is like an airplane, right? V2 is more like a rocket, and he noticed that the rocket would either blow up in the sky or would come down, close to where it was launched. And so he took a risk, and it is a big risk. He came very close to the launching pad in order to observe why the failure, of the rocket. And that's a big risk for his life, because the rocket basically, when shoot up, it just went back down to very close to the launching pad. And he observed that, in fact, the body of the rocket was so flimsy that it tends to buckle. Okay, that's one of the observations that led to really an increase in research in the development of the understanding of the behavior of cylindrical shell. So this is a vibration of the cylindrical shell that is completely fixed at the two ends. Okay, observe. So here is the street fighting intuition that every engineer must have. If you look at the two mode shapes, can you tell which mode or which eigenvector would have a lower eigenvalue? Remember, a lower eigenvalue corresponds to a longer period of vibration. Okay. So if you look at the two modes here, which one has lower eigenvalue or frequency, and which one would have higher eigenvalue or higher vibration frequency? So David and Robert.
Yeah, the one on the left is lower.
The one?
On the left is lower.
The one on the left has what?
Lower.
Lower. David, agree? Okay. Yeah, why? The answer is correct. Why?
It's not basically a lower frequency. Because it has less.
Less waves.
Yeah.
Less deformation, less waves. Okay, so higher frequency, you would have more nodes. It's called the nodes. I think maybe in the finite element course, I showed the Takuma-Melrose bridge, and there you can see, the torsional nodal line. But so that's a good observation, and keep that in mind. And now this is the case where you no longer have a rigid constraint of the two ends, but here you have what is called the contact constraint. So due to gravity, you lose contact between the shell and the ring. Okay, and so these two are the two vibrational mode shape with these boundary conditions. Okay. Now, intuition, street fighting understanding. If you compare the frequency, the vibration frequency of these two modes to the vibration frequency of the two modes above, where you have complete rigid constraint, which pair would have lower vibrational frequency? So with this, let me give you a hint, okay? And I hope that I should have time to give you a quick hint. In engineering, you don't need to really, I already demonstrated with the question from Jackie, you don't really need to use very complex Yes. Could you please write down, we have video cracking.
Use street fighting techniques.
Yeah, we're about to use some street fighting. I'm tired of that crap.
You have here K and M, right? And I'm not going to derive that, and I expect that everyone should be able to derive this equation of motion, and the equation of motion is M y double prime plus K y equal to 0. Okay? So what would be, so the trial solution is e to the lambda t, right? And if you plug the trial solution in, the characteristic equation is m lambda squared plus k equal to 0, right? After you cancel e to the lambda t. So in this case, lambda 1, 2, meaning that 2 roots, that's plus or minus square root of k over m times I, with I being square root of minus 1. And this is omega, the circular frequency. Okay? So the circular frequency is proportional to square root of k and inversely proportional to m. Okay, so that means that the stiffer the structure, the higher the frequency.
Yep.
So once you have that in mind, if you compare, if you look at this, okay, which pair is stiffer? John? Kevin, which pair is stiffer? The more constrained, the stiffer. Okay, so this one is stiffer. So these two pairs would have higher frequency than these two pairs, and
The one on the bottom left is the lowest frequency, right? It's just
yeah, that's right. And in fact, here are the numbers here. Okay, so the top two pairs, and these are the bottom. Okay, so lecture summary.
Good.